Hi everyone, Dr. J here, and in this video we're going to talk about an example of least squares regression in Python. So to start out, I've got my imports, numpy, matplotlib.pyplot, and pandas. These are the Python packages that I'm going to be using for this example. I've also uploaded a file which contains some data that I'm going to use for the regression example. And just looking at the data, you can see we have a number of columns, including this column called K, which is hydraulic conductivity, phi, which is porosity, depth, T2ML, and SOE, which stands for sum of echoes. So this is some data related to NMR, nuclear magnetic resonance. And if we just do a basic scatter plot of T2ML versus hydraulic conductivity in log space, you can see the data that we're going to try to fit. Now this particular data is a little bit noisy, and you can see it's not necessarily going to be best fit with a straight line, but we're going to start with that and see how it looks. So in order to set up our problem, what we need to do is first pull out the observations or the data that we're going to use to fit the line. So I'm going to take, in this case, T2ML, or the log of T2ML, as my x variable, and the log of hydraulic conductivity is going to be my y variable. So I'm just going to rename those so I don't have to type them out every time. And so just to make sure that we're still on the right track here, let's just replot those. Looks good. And so now what we want to do is set up our least squares regression problem. Now you can check out in some of my other videos how the mathematics works behind this. What we need to do is we need to set up our data and model matrices, as well as think about what we're going to solve for in terms of the unknowns. So our model is going to be a linear model, and this model is going to have two unknowns. So we'll have the slope m and the intercept, the y-intercept b, and so the general form of the equation is going to be y is equal to m times x plus b, and that's going to be the scalar form in matrix vector form because we have a bunch of data. It's going to be a vector y is equal to m times x plus b, where capital X here, in matrix vector form, this is going to be written as d equals g times m, where g times m, g is now a matrix, and m is our vector of unknown model parameters, and d is our vector of data. So in this case, d and y are going to be the same thing. And then G is going to be a two-column matrix, having in the first column the column of x values for each data point, and in the second column it'll be a column of ones. So this is like m times x plus b times 1. So we'll just have a column of x's and then a column of ones. So let's create our G matrix, and we can do that using the numpy.stack function. So we're going to stack x, and then we'll need a column of ones, which is the same as the length of x. And then just turns out that this will end up being a 2 by n matrix, and so we want to transpose that to an n by 2 matrix. So we have n rows and 2 columns. And so we'll just use the .t for transposing the G matrix. And then what I want to do is I'm going to print g.shape just to make sure everything looks correct, and I'm going to print G itself. So let's go ahead and run this. So here we go. Here's our G matrix. It has a shape of 142 by 2, and 142 is the same as the shape of our original data. And then it's got these two columns, where now we have a column of the x values and a column of ones. There's all those values. Notice that if I hadn't done this transpose here, then we would have had the correct values, but we would have had the wrong shape. So now it's 2 by 142 instead of 142 by 2, so we want to make sure to keep that transpose in there. And now we'll end up with the right shape. Okay, so now with our G matrix created, we're going to use a least squares solver in Python. So this is the Python function lstsq, and it's going to be from the numpy package linalg, which is a linear algebra package. And here it is, least squares solver in Python. We can look at what this least squares solver does by using the question mark. And it's going to return the least squares solution to a linear matrix problem where you have a matrix A and a vector or matrix B. And this is just exactly what our equation is, where this @ symbol here denotes matrix vector multiplication. So we just have A times x is equal to B. That's exactly what we have. G times m is equal to D. So I just want to make sure that my A and B is correctly matched up. So here A is going to be my G matrix, and X is going to be equivalent to M, and B is going to be equivalent to D, or in this case, Y. So lots of variable names running around, but here's our basic equation, which corresponds to this. And the only difference between these two equations is that this would be our ordinary scalar equation that we're used to thinking about. Here is our matrix vector form of the same equation. D equals G times M. We've created our G matrix. We've got that now. We already have our vector D, because that's just, in this case I've called it Y. Let me rename it to D just to keep things consistent. So there we go. I have a vector of observations D, and that's going to be my hydraulic conductivity values. I've got my vector of T2ML values here, which is in this case going to be my x-axis values. I've used x and 1, a bunch of 1s, to create my G matrix, and now I'm going to use this least squares solver to solve the system. So this function in Python is solving the system G times M is equal to D. It's going to solve for M. And what it's doing is the same thing as if we were to solve for this analytically. It solves the generalized inverse problem, where we've talked about solving this using G transpose times G inverse times G transpose times D is equal to our M hat, where M hat is here the estimated unknowns. It's the estimates for the unknown parameters. So our estimated M, our estimated B is going to be in this vector M hat. So this is the generalized inverse problem. Linear least squares in Python is going to solve that problem for us, and we're not going to have to calculate the matrix inverse or anything like that. There are more numerically stable ways of calculating the solution to this problem, and so that's what this solver is going to use. So what we just need to make sure is that we get the correct parameters and inputs. So let's see. First we'll get the outputs, or the returns. So here we have x, so that's going to be our M hat, the residuals, the rank, and the singular values of A, which we'll call just S. So those four things, x, residuals, rank, the rank of the matrix A, and S, are going to be the four things returned by this function. And then we'll need to give it the correct inputs, so we'll need to give it A and B, and also this rcond, which is optional. So we don't need to worry about that. So here I'm just going to give it G and D. So our A and B here correspond to G and D. And now we can simply solve this problem. And you see we have some warning related to that rcond parameter. Looks like everything worked fine though. Let's test it out and see what we got for M hat. There we go. 2 values for M hat, which we expect because we should have 1 is equal to M, 1 is equal to B. And actually this first parameter will be M, this second parameter will be B. And now we want to calculate our prediction. So let's do the prediction. So to do a prediction, what I need to do is create a set of x values here, and then predict for each x value what the corresponding y value would be. So let's go ahead and do that. I'll call that, let's see, capital X, I guess, since I've already used lowercase x. And I'll just do linspace. Let me look at the range of x here. Looks like we go from about -2 to about we'll say -0.2. All right, and then our y, maybe we'll call it x prediction and y prediction. So now our x prediction and y prediction, well, in order to get y prediction, we need to actually create a new G matrix where we use our new x prediction. And maybe I'll call this G prediction. So there we go. There's my new predicted x. Here's my new predicted G. Looks like the shapes are consistent, so that's good. That means it seems to be working. And now I can say that my y prediction is equal to my G prediction times my M hat. So this is the predicted y values for the new x values here, the predicted x values, and using the parameters that we just solved for. Now, if I try to do this multiplication sign, that's not going to work because that's not matrix vector multiplication. You guys know that this is a special type of multiplication. So I'm going to do np dot dot. So this is the syntax in Python for taking a matrix vector product. So if I do this now, that looks like it worked. And then I can say, let's create everything on one plot and see how our prediction looks. So we'll plot the original data, we'll plot our prediction, and let's say some labels. And see how we look. Okay, so this is now our least squares solution for the best fitting line in estimated using Python for this relationship between T2ML and hydraulic conductivity. So if we were going to make a prediction now for what the relationship is between these two variables, we could use this line and know that we're doing the best possible job with a linear model based on this data to predict hydraulic conductivity from T2ML. And in this case, T2ML is coming from an instrument which is measuring this particular quantity, and we might want to estimate what the hydraulic conductivity is, and so this line would allow us to do that. This is the best fitting line for this particular set of data and for this particular linear model. Now, looking at this, we can also look at the residuals. We can take the predicted data for each one of the individual data points, and now let's put our original data on behind that. So we've got our predicted data now, and we don't want to plot the original data, we want to plot the original minus the predicted. So this is basically plotting the residuals. So now if we plot this for each data point, we'll see the difference between the linear prediction and the actual observations. Now, a couple things to note. First of all, we should see that the average is pretty close to 0, because remember, this is the best fitting line. The line that we've plotted here is the best fitting line. We've solved for what that is. And so the average misfit, or the average residual, should be right at 0. So if we were to do a histogram of these, it should be pretty close to 0. Another thing that you notice is that some of our assumptions might be invalid with this data set, because you see it looks like there's a lot larger variance of the smaller T2ML values than at the larger T2ML values. And so we might want to consider using some other type of fitting method other than just ordinary least squares to fit this data to account for this heteroscedasticity, which is basically changing in variance with x. So as T2ML changes, it seems like the variance in the y values change. And that's an assumption that linear least squares says should not be the case. Something else to note is that it looks like there might be some actual trends in these residuals. So you can see here we sort of are going in one direction below a certain level, about T2ML is equal to minus 1.2. And then above that level, we're kind of going in another direction. So it looks like maybe there's some other variables going on here, something else is in play. Perhaps these are from different locations, or it could be any number of things. And so this is where we would start to do more in-depth analysis and look at other types of models. Now, speaking of other types of models, I do want to show you guys how we might improve on this, or not necessarily improve, but do a more complex model. So here we've created a G matrix associated with a linear model. Here's our original observations. So we can just as easily create a G matrix with any other type of model using this approach. As long as it's a linear model, we can do it. So for example, we could try doing a quadratic model. So let me copy and paste this all down here. So now we have two unknown parameters, m1 and m2, and we still have our y-intercept. Our model now is going to be m2 times x squared plus m1 times x plus b times 1. So we're still going to say d is equal to g times m. That equation doesn't change. But our G matrix now is going to be slightly different. We're going to add in a column where now instead of a 142 by 2 matrix, it's a 142 by 3 matrix, and we've added an additional column, which is just this x squared column. So now we have x squared, x, and 1, and we're going to find the 3 parameters, which are the best fitting parameters, which will allow us to fit these data the best with a 3-parameter quadratic model. And we've been able to do this by simply modifying our G matrix. Everything else stays the same, So we're going to do the same exact thing. We've just created a new G matrix. We've solved now for these new parameters. We can look at what those are. So there's our 3 parameters. Let's see how well they fit. Here's our prediction. And we'll look at the residual scatter plot again. Okay, so now you can see we've at least corrected one of our problems. With this quadratic model, we've been able to more or less remove the trends. We're still centered around 0, but you don't see those trends anymore like we had before. And let's go ahead and make a new prediction of what this model would look like. So our predicted G in this case is going to be, again, same as before, except now we're just going to add a square term. Okay, there we go. There's our predicted G and our predicted Y. And now we can make this plot. So here's our best fitting quadratic model for T2ML and predicting hydraulic conductivity. Now, a couple things to note about this model. You see, first of all, that it does seem to kind of go through the data a little bit better than the other linear model does. Although you do see something a little interesting. You see that this model starts to go back down, so the increasing trend here reverses, goes back down as you get to higher levels of T2ML, and that's not necessarily something that's physically realistic. So something important to keep in mind is as you add more complexity to your models, so you could continue on and add a cubic term or a quartic term, you could add sines and cosines, all sorts of things can go into this G matrix. And the important thing is that your models, whatever model that you're doing, can be justified in some way. So in this case, perhaps we have more confidence in the linear model, even though it doesn't fit as well, because it has some overall behavior which we think is more realistic. On the other hand, if you're only worried about predicting within a certain range, then this quadratic model would probably work just fine. If you knew that you weren't going to ever see values greater than negative 0.5 in this case, then probably this quadratic model would be a sufficient way of making that prediction. Okay, so that's an introduction to least squares regression in Python. Like I said, this is entirely extensible. You can build all sorts of different types of models. Really, any linear model can go into this G matrix. And once you have your observations, you can use this syntax to solve for what the best fitting parameters of that model are, and then use that to make new predictions of new observations. And you can also do hypothesis testing and uncertainty quantification on those parameters, and we'll talk about that another time. All right, that's all for now. I'll see you next time.